Hello everyone. Okay, so we are on page 16. Page 16. Okay. Page 16, and we're covering topic 5.3. And in class last time, we learned about how reactions can be zero order, first order, and second order. And today we're going to learn how to look at different types of graphs and identify it based on the graphs if a reaction is zero, first, or second order. So I need to make an update. First, do you see how each of your graphs say concentration versus time, concentration, concentration versus time? Will you change the second graph to be ln, natural log, for concentration versus time? And then the third graph, I need you to change it to inverse concentration versus time. So you could write that as either 1 divided by the concentration or concentration raised to the minus 1. If a reaction is zero order, and let's go back to this base reaction we've been talking about when reactant A turns into product B. So the rate law of this guy would be rate is equal to K concentration of A. And if it was zero order, well, anything raised to the 0 is 1. So this is the same as rate is equal to K. And here's what we see happen. If I were to take a reaction that was zero order and I graph the concentration versus time, we get a linear graph here. And what's cool is the slope of this line, the slope of the line is going to equal the opposite of K. It's going to be negative K. So if we have enough information to get what the slope is here, then that is equal to our rate constant, K. In last class we learned that the rate constant K for zero order is going to have units of concentration versus inverse concentration, inverse time units, time to the minus 1. And that makes sense because we have rise over run. That's how we would get our slope, concentration or molarity divided by time. Okay, now if it is zero order reaction and we graph the natural log of the concentration, we actually get a curve instead of a linear graph. We get something that looks somewhat like that. So it's going to curve. So if it doesn't say zero order and it shows you a concentration versus time graph and a natural log versus time graph, and it is linear for concentration versus time, that's how you know it's a zero order reaction. Again, if it was zero order and it was an inverse concentration versus time graph, we get something like this. Okay? So zero order gives us a linear graph when it's concentration versus time. What's cool is if you look at your reference guide, if you pull out that blue paper as our reference guide, there's a section on there that says kinetics. Like I copied this right from the reference, okay? And underneath kinetics, there's 1, 2, 3 equations, and then there's an extra one down here. They've put these in order. They didn't label them, but they put them in order. This first reaction only works when it's a zero order. The second one is for first order reactions, and then the third one is for second order reactions. So often in AP Chem, they first show you these graphs and then it causes you to realize, oh, concentration versus time is linear. This must be zero order, and then the next step would be using this equation to solve for one of these things. Either the concentration at some given time minus the concentration at time 0 at the very beginning minus negative K multiplied by whatever that time was to get this concentration. Now, what about first order reactions? So we're going to update the graphs again. This was concentration versus time. The second one, will you make it ln, natural log versus time, and then the last one is inverse concentration versus time, or concentration to the minus 1. Okay. Now, when it is first order, not second order, we know that our rate law would be rate is equal to K concentration of A raised to the first. And often we don't have to write that down, right? So I'm going to show you 3 graphs. The concentration versus time graph when it's first order usually looks something like this. Like it's curved and it's decreasing over time. I didn't draw that very pretty, but that's what we would see. Okay. When it's first order and we have a natural log versus time graph, you get something like this. And when it's a first order and it's an inverse versus time graph, we tend to get something that looks like this. Okay. So, what's cool about this is they'll often show you 3 graphs: concentration versus time, natural log versus time, inverse concentration versus time. And you have to figure out, you have to visually look at it, which one is linear, which one is not curved. Oh, it's natural log versus time. That only happens for first order reactions. And just like before, the slope of this line is going to be equal, so the slope of this line is going to be equal to the opposite of what your rate constant is, K. So you can use a graph to solve for K if they give you enough information. And like we said before, this first equation only goes for 0 order. So if this is the graph I'm getting, I am not using this equation. The second one is what goes with first order. So this is what I would be using right there. The other cool thing about first order, so you know, like radioactive decay. Radioactive decay is a first order reaction. And just a reminder, and especially for anyone that doesn't know, the way that we measure radioactive decay is something called half-life. Okay? And what we mean by half-life, I'm looking for like a colored piece of paper to explain this. Oh, perfect. Sticky note. Okay. Let's say that this is my radioactive substance, and this is how much I have at time 0, right at the beginning. Okay, so this is what I have. And let's say that the half-life of this radioactive substance is 1 day. So 1 day passes, and half of this material will decompose into its, what do they call it? The daughter product, that it goes from this radioactive substance, it experiences nuclear radiation, and then that changes this substance into its daughter product. And half of the atoms in here are going to do that. So initial time, 1 day, which is the half-life of this substance, 1 day, and half of this radioactive substance is still radioactive in the original thing, and the other half has decayed and turned into daughter product. Okay. Now, that was 1 half-life. 50% of it is gone. Okay. The second half-life, that's another day. So this is after, we're ending day 1 with this much. Now we have a second day. So a second day happens, and half of these atoms are going to decompose, usually into a more stable and sometimes not radioactive daughter product. So this is how much is left after day 2. And we keep going, going. After day 3, there's half of that, and after day 4, there's half of that. So when we have radioactive decay, here's the initial amount, and after 1 day, half of that is gone. After 1 half-life, half of it is gone, turned into something else. After a second half-life, half of that is gone. So we're left with a fourth of the original substance after 2 days. And we see this 2 half-lives. We see this on the graph here, that I started with a concentration of 1. And then I go, what's half of 1? That'd be 0.5. And when I go to 0.5, I see that it took a single half-life, 1 half-life, for half of this to go away. Now, a half-life is the same amount of time. So if this was 2 hours, then if 2 more hours happen, so the same amount of time is going to pass. Now I have, half of that, because I went from 0.5 to 0.25. Okay? And so then we're going to do another half-life. So there'll be another 2 hours, or whatever the half-life is for this substance. And we're going to go from 0.25 to half of that, 0.125. Okay? And so when it's a concentration versus time graph and it's first order, it is not linear. We get a curve, and we can track this curve. If the same amount of time is happening and half of the material is disappearing with each chunk of the same amount of time, then this is a first order reaction, and this is how radioactive decay works. Okay? This leads us to our second really helpful equation, and it's right here. This one only works for first order. First order and first order, and this is our half-life reaction. So to figure out the half-life, how much time it takes for half of the reactants to decompose or turn into a product, you take 0.693 and you divide it by the rate constant. Okay. That will tell you your half-life. All right. So find the half-life for the following reaction. And we have a natural log versus time graph. Okay. What's the slope of this line? Because the slope will equal the opposite of what K is. So it's our rise over our run. Okay? Another way of thinking about this would be so rise over run. Or what is the natural log of the concentration final minus the natural log of the concentration initial, or at time 0, divided by time final minus time initial. And if I look at this, this is the natural log already, so I don't have to take the natural log of this. We ended with -5. That was my final natural log of the concentration. And I'm going to minus this from where it started, -4. And then I'm going to divide this by the time. The time final was 600 seconds minus my initial, which was 0. Grab my calculator. Okay, plug this in. So -5 minus a -4 divided by 600. This gives me -0.00166 repeating. Now remember, the slope of this line is equal to -k. So if we take the opposite of the slope, that's what k. Okay, everyone, sorry, my camera stopped working, So now I'm going to have to like combine the two videos, so sorry if there's like a bit of a jump here. So I took the opposite of the slope, that's my K, and last class we learned that when it's first order, the units for K is just whatever the time units are, raised to the -1 or inverse time. And the time units is seconds, so it'd be seconds to the -1. All right, great. But the question was find the half-life. And we saw an equation. We saw that to figure out the half-life, what we do is we do 0.693 divided by K. So 0.693 divided by this K value, and this was 415. Again, I'm grabbing numbers from here, so it's hard to do sig figs. So I'll just get one digit after the decimal, 4.158. But of what though? Because half-life is how much time it takes for half of the substance to decompose or disappear. And this had units of inverse seconds, and we're taking something unitless and we're dividing it by the inverse of that time. And so it flips it back up there, so this is in seconds. So the half-life of this substance, half of this will decompose in 415.8 seconds. All right, last one, second order reactions. So updating our graphs just like before. We had a concentration versus time, then I want you to change it to natural log versus time and inverse concentration versus time. Okay, for a second order, what we see is that the concentration versus time and the natural log of the concentration versus time are both curved. Usually the concentration versus time of a second order is like steeper curve, and then it tends to like shallow out a little bit. And the inverse concentration versus time is our linear one. Usually goes like this. Okay, now because this slope is positive, what we find is the slope of this line is actually equal to K instead of negative K. The other cool thing about this is if I don't tell you that something is second order, but I give you these three graphs, the one that is linear is what tells us the order. So anytime an inverse concentration versus time graph is linear, that's when we know it's a second order reaction. And just a reminder, when it's second order, this rate constant K has units of, so units of K, the units of K are equal to molarity to the -1 time to the -1. Inverse molarity, inverse time. And just like before, in our reference guide, we know we're not using the first one because that's zero order. We know we're not using the second reaction or equation because that's first order. This only goes with first order as well. So we would be using our third order reaction, which is the inverse concentration reaction right there. Great. Okay, so here's an example. We are given data here, and it looks like we have an inverse concentration versus time and a natural log versus concentration. Sorry, natural log of concentration versus time. And this is our reaction. We want to know what the rate law is. So rate law, rate is equal to K, and we only have one reactant here, NO2, and we have to figure out what the order is, and we're going to base it off of these graphs. So when I look at these graphs here, I go, oh, my inverse concentration versus time is linear. And that is the case when it's a second order reaction. So this must be rate is equal to K, concentration of nitrogen dioxide squared, or that's the second order. Okay. What is the rate constant? Okay, so they give us a data table, but they don't give us info here. And this is concentration. This is not inverse concentration. So I'm going to use this third order reaction equation right here. And in this one, it says that if I take 1 over the concentration of nitrogen dioxide at some given time, and I subtract it from 1 divided by the concentration of nitrogen dioxide at time 0, that's going to equal K multiplied by this time. And so in this table, I have my 0 and I have these times. How about I just pick like I need this one, the 0, but then I'll just do this final trial there. Okay. So 1 over the concentration at this time, and the concentration at that time was 0.0057. I'm going to minus that from 1 divided by the concentration at time 0, and the concentration at time 0 was 0.070. But I'm not solving for K multiplied by T, I'm just solving for K. So how about I divide both sides by whatever this time is. So divide that by the time, which was 3 times by 10 to the second, okay, or 300, same thing, seconds. Great. Let me plug it in. So top of my fraction, 1 divided by 0.0057 minus 1 divided by 0.070 divided by the bottom of the fraction, which is going to be 300. And so K is going to equal, and this was 2 sig figs. This was 2 sig figs in the table here. And then this one was 2 sig figs. That was 2 sig figs. So I'm going to do 0.54. And this is second order. So my units of K are going to be concentration to the -1 and time to the -1, but time was seconds. So molarity, inverse molarity, inverse seconds. Right. Great. Okay, that wraps up what we're going to cover in this video, and during class we will do some practice problems on this. Thank you, everyone.